Hi everyone. So far we were discussing upon a full converter, that is fully controlled bridge rectifier with R, RL and RLE loads. So there we have seen that the load current I0 will always be unidirectional in nature because the thyristors or the SCRs are unidirectional conducting devices. But we have seen that the voltage, output voltage can have a positive polarity or a negative polarity. Therefore, we can say that a full converter is nothing but which is operating a two-quadrant operation, that is with voltage positive or voltage negative, and the current is in the always positive. So that is known as a full converter. And full converter is employing all the devices which is used in the case of a full converter are thyristors or controlled devices or SCRs. Now in the case of a semi-converter, we will be using a mix of thyristors and diodes, and the semi-converters are devices which are having a one quadrant operation, that is the voltage and current are always positive. So it is not possible to have a negative voltage during the operation of the semi-converter. So now we are going to discuss about the semi-converter with R, RL and RLE loads. So all these discussions are somewhat same with the full converter. The only difference is that we are using two diodes in place of the two thyristors in the lower half of the system. So now we are having two thyristors and two diodes, T1 and T2 and D1 and D2. So four devices are there, in that two are SCRs and two are the diodes. So during the positive half cycle from 0 to pi, the thyristor T1 and the diode D1 both are forward biased, and the rest of the two are in the reverse biased condition. Now, even though the diode D1 can conduct during the positive half cycle at any time between 0 to pi, the total conduction current path is taken through the thyristor T1. So T1 has to be gated or triggered on in order to take the conductance from the source to the load through the devices T1 and D1. Now just imagine that I am going to fire my thyristor at an angle alpha. That is, T1 is being triggered at the angle alpha. So this is marked as your alpha. Then the entire source voltage will be appearing across the load, and therefore I can plot the output voltage waveform like this from alpha to pi. Now during this period of time, the current will also follow the same convention of the voltage V0 because it's a resistive load. During that time, the source current Is is also flowing in the same direction of your I0, and therefore I can plot Is also like this. Then from pi to 2 pi, or when the voltage, source voltage Vs goes beyond the angle pi, the thyristor T1 and the diode D1 both are reverse biased. So therefore, since the diode D1 is already reverse biased, then the device will stop conducting, and therefore the load current will not flow through the diode D1 and the thyristor T1. And then again at any instant of time, I can trigger the thyristor T2, which is forward biased from pi to 2 pi, and at pi plus alpha, I am going to fire my thyristor T2. So the load voltage will be same as the source voltage. So during that period of time, the load current will also be in phase with your output voltage V0, like this. But how the source current will be looking like? The source current will be moving from the point B to T2 to R through D to A, and in the opposite direction of your current Is. So your source current will be in the opposite direction of your load current I0. So the same sequence will be repeating for the rest of the system. Now we need to plot the thyristor voltage. So if I am plotting the thyristor voltage for the T1, so when T1 is on, from alpha to pi. So during that period of time, voltage across the thyristor is 0. The rest of the time it is nothing but the source voltage which is appearing across the device. Now we need to also find the output voltage V0. It is 1 by pi under alpha to pi Vm sin omega t, which is nothing but Vm by pi into 1 plus cos alpha. In the similar way, you can also write down the equation for I0 and also for V0 RMS. The kind of derivation is same which we have already discussed in the earlier cases. Hi everyone. Now we are going to discuss a single phase semiconverter with an RL load. So in the case of the RL load, you have your current which is lagging behind the voltage. Now we can have our focus of interest on VAB and VBA, which is nothing but the voltage across the points marked over here, VA and VB. So VAB is positive from 0 to pi, or I can say that VBA is positive from pi to 2 pi. So just reverse the waveform for our ease of understanding. Now from 0 to pi, I can fire the thyristor T1 at any instant of time, and T1 is already in the forward biased condition. So at the angle pi, I am going to fire my thyristor T1, and therefore the load voltage will be same as the source voltage. Now, since it is an RL load, the current I0 will be gradually, it will be increasing. And then it starts reducing. Now, it will not reach to 0 at the instant of pi. So therefore, the current starts to flow like this. And since the current has not come below the halting current, thyristor T1 will remain in the on condition. Now, when the voltage, source voltage is passing after the angle pi, what happens is that the point B is becoming more positive when compared to the point A. And therefore, the diode D2 gets forward biased through the diode D1. And therefore, now the conduction of your current is from T1 RL D2. So now it is acting like a freewheeling path for the current to flow. So I can say it from pi to the next firing angle, which is pi plus alpha. I can say that there is a freewheeling path which is appearing across the load. And this will make your output voltage V0 to be 0 from pi to pi plus alpha. Now again, between pi to 2 pi, the thyristor T2 is forward biased, and I can trigger on the thyristor at any instant of time. Now just imagine that I am going to fire my thyristor at pi plus alpha. That is, thyristor T2 is fired at pi plus alpha. Now what happens is that the current will be flowing from T2 RL D2 back to the supply. Okay. That means whatever the current which was carried away by the thyristor T1, now it is being transferred to the thyristor T2. And since there is a transfer of current from T1 to T2, therefore thyristor T1 gets commutated. Now the new conduction is from the thyristor T2 and the already conducting D2 during the freewheeling period. So therefore I can plot the output voltage like this. So what happens? The current again, it will start increasing. It will start reducing like this. So that means from it was conducting till 2 pi. So after 2 pi, what happens? After 2 pi, the point A is becoming more positive when compared to the point B. Therefore, that will result in a freewheeling path for the current through flow to the thyristor T2, the load, and D1. Now it is flowing like this. So that means the load is being have a short circuit path for the current to flow, and therefore the output voltage V0 becomes 0 again. So now that sequence will be repeating for the rest of the cycles. So now I can also plot the devices which are conducting. So during this period it is T1 and D1. During this period it is T2 and D2. This is again T1 and D1. Now, which device was conducting during this period? It is T1 and D2. During this period, it was T2 and D1. Again, during this period, the devices which are conducting are T2 and D1. So that will be continuing. Now we are going to plot the source current IS. From our earlier discussions and what we have discussed now, we have seen that during the positive half cycle, the load current I0 and the source current IS will be flowing in the same direction. And then during the negative half cycle, the direction is opposite like this, and therefore I can plot the source current in the opposite way of your load current I0. So that will be continuing. Now, in the same way, you can also plot the thyristor voltage VT1. So from alpha to pi, T1 is conducting, and T1 is remaining conduction from also from pi to pi plus alpha. So during time it is also 0. At pi plus alpha, T1 is getting commutated. So here you can plot. Now, in the same way, you can also plot the average output voltage V0, which is again nothing but 1 by pi integral alpha to pi Vm sin omega t d omega t. This is nothing but Vm by pi into 1 plus cos alpha. So these kind of derivations I will not be doing it because it's a simple mathematical operation which we have already studied. Now there are sometimes we can also say that this is for a very high value of inductance, the load current I0 can be more constant. So more constant means we can plot this I0 as a constant value like this. So for ease of explanation, I have, for understanding the purpose, I have noted down it as a medium value for your inductance cell, so that there is a variation in the current, or else I can plot the current as a constant value. So that is our discussion with the single phase half controlled. So it is half controlled, not halfway controlled. It is half controlled semi-converter bridge rectifier with RL load. Next section we will see the RL E load.